Tanya, are you there? Tanya, can we start?
Yes, ma'am, I think we should start.
Okay, please start.
Okay. Welcome back, dear audience. We hope you enjoyed your break and are now re energized and ready to delve into the second half of our session. So, without further delay, let's dive right into the exciting session that awaits us in this segment. I am delighted to introduce Mr. Srijit Mukherjee, a machine learning researcher at Penn State University, whose journey through data science is nothing short of remarkable. Armed with strong foundation in statistics from the Indian Statistical Institute, Kolkata, Sir has ventured into diverse dimensions of data, from tabular intricacies to brain image mysteries. His unique perspective, transitioning from statistics to computer science, enriches his approach to data challenges. His passion extends beyond research. Over the years, he has mentored and guided a diverse group of individuals, helping them master statistics and machine learning. In this era of rapid technological change, he is committed to giving back to the community and nurturing future data scientists. It is our privilege to share this platform with him, as he is about to share with us his knowledge and expertise in the subject matter. So the platform is all yours.
Yeah, thank you so much, everyone, for attending this. And thank you, Audience of Technology and Professor Chakraborty, to invite me here. Thank you, Professor Balki, to also introduce me in such a beautiful way. It's been an honor to be here. However, I wish that I was present there with all of you to discuss and share all these ideas. Let me just share my screen before I start. So, since we are not there physically together live, as I've talked about discussing and sharing ideas, which I personally think is the best way to learn something, I would really appreciate if but I'm sure I would love to if you have doubts over this, if you send your doubts over this Google Meet. In 2019, I attended my first deep learning workshop just like this, I think, yeah, quite a few years ago. And unfortunately, I couldn't understand anything out there. Like, you know, not like I could understand the mathematics, how it's happening, but I couldn't understand why it's happening, like the story behind it. And you know what's that's called the real understanding. I do not want it to happen to you right now in this workshop. And I believe from my personal experiences that the only way it's possible is to ask and look for questions that you have inside of you for this specific topic and seek answers to them. For example, just like you learned or you really get excited or got excited when you learned why the sky is blue. Very simple questions. Or why does the fire always goes up? Similarly, the idea of neural networks for the engineers and associated research methodology. We will start with a very fundamental question and we will slowly proceed step by step. We'll probably not learn like the entirety of deep learning. Even I don't think it's the purpose of this short um, discussion. So let me start with a very fundamental question. And since everything we are doing for data, let's look into some data set. So there's a picture of a horse and some audio signal, and you can see that there is some cells data set of a export import company. And if I ask you this question, guys, that can you find the pattern in this data, in the data of a horse picture, an audio signal, and an import export sales data set? I would love to know if you have any uh, understanding or if you want to share your views on this. Anyone from this audience? What is the relation? What do you think is the relationship between this picture of horse and audio signal? What is the pattern and the export import data? Anyone? I will just wait for a few seconds before I continue. Okay. So the basic idea is this, that there is no relationship you can find. There is no pattern. Now the question is, all these days we have understood, we have thought that the more the data, the better it is, right? That's what the buzzwords are all around. The more the data, the better it is. However, this shows you that it is not true. I mean, you can add pictures of cats, dogs, tigers, lions, and you can add different artist songs, and yet you cannot find the pattern. So data never comes alone. In fact, data alone, just data alone, is very powerless. It's not at all powerful. There is zero power in data alone. Now, there is a gap in understanding, like, okay, so what did we learn all these days? And that's why you should understand that we are using data to solve human problems, human issues. So data should always be accompanied. Data is never alone. Data should always be accompanied with questions. Questions that human beings, that you want to ask. Just like I started with. Questions that, can we make an app that can recommend us songs based on our previous song experiences or movies? So questions that are there inside of you that you really wanted to know as a child. So data always comes with questions. Now, let me try to give you an example with a scientific perspective. So it starts with a question, then you collect data in a proper way, you transform the data to make it easy to find patterns, And then using scientific tools, real scientific tools, you try to solve that specific question or questions. As an example, let's take Boyle's law that we have all learned in our school days. We have done experiments. I hope you remember if you have a physics lab in your school days. So Mr. Boyle asked the question that, hey, do you think there is a relationship between pressure and volume? And he asked this question, and that question was inside of him. And that question led him to ask people around, discuss, and they together collected data on pressure and volume. That's the only way they can validate their hypothesis. And you can see the picture of volume and pressure on the screen. And then they visualize it, as you can see on the left hand side, this one. And after the visualization, they use their human intelligence or models out there to find out a relationship that it's inversely proportional. So you see that a Boyle couldn't have answered this question, rather couldn't have thought about collecting the data set if he didn't have the question in the first place. So it always starts with question. Now, in the history of machine learning, data science, statistics, there are two fundamental questions that people have been asking, and they have boxed them into two categories. What are those two questions? The two questions are of the following nature. Number one, what is the relationship between x and y, like two variables that you're interested in, pressure and volume? And how does a set of variables or a certain data behave? What exactly do I mean by this? Let me explain. For example, you ask the question that what is the relationship between pressure and volume, x and y? And the second question is like, you take x, a variable or a variable set, and ask which countries have similar type of hair color, height, and weight. That is, together is called x. Which countries have that? That means it's asking about similarity, rather grouped behavior. The first one, where we seek the question of relationship, that is called supervised learning, the relationship of x and y. And in the second question, where we are seeking the answer to the behavior of a set of variables or a variable x, it's called unsupervised. Let's understand both of these questions, both of these learnings. In a bit of depth and details. However, I will take a small detour from here to explain to you something very fundamental, which I have not used my slides for. People are mostly from informatics background, I believe, and they have been, and of course, you guys are going to be engineers, so most of you are expected to know some coding according to the coursework, I believe. So there's a fundamental difference between learning and instructions, if you believe. So let's take a small example. Now there's a word learning over here, so I'm trying to use this opportunity to explain to you well. So what is the difference between instruction and learning? In instructions, let's say you have a starting point A and an ending point B. and let's say your mother says go straight and then left and then take a right, or go straight, walk for 50 hands, go left, walk 70 hands, and then go right, walk 100 hands, and you will reach your destination. This is called instructions. You're instructing specifically to a person or a computer or a machine that do this, do that, and you will reach your destination. You will complete the procedure. You will successfully accomplish the task you set out for. However, learning is a bit different. Learning is exactly how you learned how to draw the alphabets. Let's say your mother has shown you, okay, these are examples. This is A, this is A, this is A, and she has drawn probably hundreds such letters on your paper, probably using your own hand and showing it to you. And that's how you learned. She didn't tell you, draw the first line at a 45-degree angle and the second line at another 135-degree angle, and then take the midpoint of that and join the midpoint of these two lines. That is not how she taught you. She taught you probably using examples and examples and examples and examples and examples, and that is the difference between learning. Probably the end goal, the end, whatever you have drawn, the actual thing and the end thing, they are the same. But this is learning by repetitions, and this is learning by not learning, but that is instruction. So this examples of data, learning from the examples of data, that is the goal of the whole data science, whole statistics, whole machine learning community. Learning by examples. And learning by examples, and that's why supervised learning and unsupervised learning play a really big role. So let me explain what is supervised learning to you and unsupervised learning to you, and then we will move ahead into much more details. Slowly the math is coming into the picture, step by step. So there is data. Let's take a data set is a tabular form. I will give more examples, do not worry. And you can divide the data set into two halves. Let's say predictor variables, the future variables, which are all the independent variables, and the response variable, the dependent variable, which is dependent on the predictor variables or the independent variables. We name the response variable y and the predictor variables x. X can be a group of variables, remember. Now the question of supervised learning is that if I give you new predictor, new features, will you be able to find or predict the corresponding y response variable? This is the question of a supervised learning approach. Now you have x, you have y. The goal can be reframed or rephrased as finding the function that models the relationship between y and x. Now, if you know this function, if you know this relationship, because understanding supervised learning, you're modeling, you're understanding the relationship between x and y. So mathematically, if you want to translate into mathematical language, you have to use mathematical language of relationship, that is function. Function is the mathematical modeling of relationship, of encoding the ideas of a relationship, mathematically representing the ideas of a relationship. So y is equal to fx, where f captures the relationship between x variable and y variable, x variables and y variable. Goal of a supervised learning method or algorithm or an approach is to find this relationship between x and y. How to do that? That's an upcoming question. We will look into that in much more details than it's here. Do not worry, math will come and come. I don't know whether you want it or not, but it has to. Now let's come to the unsupervised learning approach. In unsupervised learning approach, you have data, and you have just X, the features. Okay, X, the set of features. Let's say hair color, eye color, height, weight, BMI, whatever. BMI is body mass index. Now you take this data and you plot it. So of course, understand that there is a small error in this whole thing, and uh, it was just for visual purposes. Here, the dimensional data set, you can see that each column represents a different data set. So there are 9 different features out there, but I have plotted in 2 dimensions. So assume that there are 2 features out there. I am plotting it, numerical features. And you can see, if you plot it like this, you can see that certain group behave together. That is exactly what I mean by behavior. Certain group cluster together, certain group tend to behave similarly in a similar manner. And that is one of the goals of unsupervised learning, where you want to capture and mathematically model this group behavior, this clustering behavior. So you see, the word behavior is coming, the relationship is not coming. The word relationship is not coming into this picture. So we are trying to find grouped behavior of this data set, right? This is one of the fundamental goals of unsupervised learning. Let me give you some examples. Let's start with supervised learning. Sorry, it's just my morning, 5:30 a.m. I have to have some coffee to stay awake. So as you can see on the data, on the screen, the data set. This is a data set of a wine, red wine, where there are many different types of wine. You can see the class identifier, although it's all says one, it's a part of the data set. It has different types of wine, and that is the response variable. What type of wine are there? Probably there are different companies or different types. And the features you can see are the different chemical compositions like alcohol, malic acid, ash, the alkaline nature of ash, magnesium, total phenols, flavonoids, and all these aspects, all these chemical features. The goal is to find or predict the type of wine or which company's wine it is, or the type of wine from the chemical composition. The question is mainly, are the different types of wine having different chemical compositions? If yes, what is the relationship between the chemical composition and the type of wine that you are looking into? However, I will transform this dataset into a different dataset by small perturbation, and you will see how it instantly changes into unsupervised learning because of the question. Now, what I do is I just remove the class identifier column. We do not know, let's say that we do not know the dataset or the data of which type of wine it is. We do not know that. In that case, what does this problem boil down to? This problem boils down to the following question, that can we identify different clusters of wine, different behaviors of wine? Because you know that different types of wine will be having different chemical compositions. So you know already from the dataset, but assuming that prior information you have, you can understand that yes, certain groups of wine will cluster together, certain data set will cluster together, this data set of chemical compositions, because they correspond to different wines. So you see, instantly, by changing the response variable, by removing the response variable, you can transform the whole data set into an unsupervised learning, because the question is different now. I hope you have understood this fundamental difference between unsupervised learning and supervised learning. Is there any question out there till this point of time? Did you understand? What did we discuss till now? Data doesn't come alone. Data always comes with questions. Questions are of two formats: supervised learning, unsupervised learning. I've explained what a supervised learning is with a small mathematical aspect and an example, and I explained what an unsupervised learning is from a small mathematical idea, graphical idea, and an example. Any questions out there? I would love to hear that.
Is
Uh,
there any question, students? I guess there is no question.
okay. So now we will just focus on supervised learning for the time being. For supervised learning, we will start with one simple model. Let's say you have a data set of height and weight, as you can see on the screen. The x-axis is the height and the y-axis is the weight. I think height is in, I'm not sure what is the unit of the height or the weight. Weight probably can be in pounds, but I'm not sure about the height. You can see the data set on the screen, as I have told you, on height and weight. Now you want to model the relationship between this height and weight. So you can probably understand that you want to probably capture the notion that as height increases, weight tends to increase more. Now the question is how? Is it increasing? Like how it's increasing? So you can find two models out there, like three models. You can say that okay, by this blue line it increases in that way. By this red line it can increase. By this yellow line it can increase. How? Or by this one it can also increase by this way or by this way. There are many ways out there. The question is that we will first assume that it's a linear function, linear increase, because it looks linear and it's a simple model. We have assumed that. Now, given that we are looking into just linear equations, which linear equation really explains the relationship between height and weight? We have many candidates for that. We have infinitely many candidates for that. You know that, of course, this is not a good candidate. Now, the question is why? That is something you should ask yourself. Why this is not a good candidate? What makes it different? So what we need is that, let's say, just like the professors grade you for every person out there, measures they measure the performance of a student by a single number, let's say a grade or a single GPA or CGPA, I don't know, percentage towards the end of the semester. And based on this number, they probably say that okay, this is the best student out there. They give an award. Similarly, we want to extrapolate that concept to judge, to understand, to model, to find which algorithm, which line works better. So to each one of them, we want to assign a number and we will find that line. We will use that line that has the minimum such value, which is called the loss function. it should be, if you take the minus of loss function, it's maximizing. Now, the question is that how will you measure what is exactly a loss function? How will you measure the performance of this line? And let me introduce to you simple linear regression. Therefore, okay, this is quite a different way of introducing simple linear regression, but let me try it out. As you can see on the screen, that we are taking the height and weight of a few people. Probably you can you know the names of the people on the left hand side, and the height I have taken it to be in feet and the weight is to be in kg. And if you have this data set, I organize it in this format as like a table. Now, there's a lot of things out here. I should explain it to you in small steps. So we have this data. We input in this, like this is the input here, the data set. Just give me a minute. Now, when you're starting to find the relationship, it starts with a model assumption that in this case, you have assumed that it should be a linear equation. You could have assumed it could be polynomial. You could have assumed it could be exponential. You could have assumed it could be a constant function. But that is an assumption that comes from the domain knowledge. And domain knowledge is equivalent to understanding more and more data. We have seen the data set of height and weight of individuals, and we have the domain knowledge that it's probably simple to have a linear equation modeling. So we say that the y, so x is the height. So we say that the weight is dependent on the height. And we assume, this is an assumption, that it's a linear equation. We assume that. That's a very basic fundamental assumption. It's assumed from domain knowledge. You cannot question this. You can only question this when your domain says so. Okay. By not questioning this, I mean, you have to fix it in the first place. You cannot change it in the middle. You cannot ask yourself, why did I select this model like in the first place? You have to be very sure while selecting this model. Now, once I've selected this model, observe that we need to find something which is called loss function that actually tells you that it really focuses on the relationship. It really encapsulates the relationship between x and y. Now, how do we measure that? Let's go to back to the example. If you take this red line, you can probably understand that it measures well if it's not too far away from the actual data points. If the red line, that x comma y of the red line, in other words, in other words, if you take this point here, the predicted is this red, this one, and there are a lot of points out here. This one, this one, this one, this one, this one, this one, a lot of points out here. The difference should not be large. For example, here the difference is large. But there is another issue that if you want the difference to be small at this position, the difference can be large at this position. So you have to make sure that the difference is small for all the points out there. the difference from the actual point and the predicted point. This is a predicted value, right? The actual point and the predicted point, this should be close, not just for one data point but for all data points. And accordingly, for example, that's the idea of democracy, right? You want the voting system to be average of all the votes that is received, right? Not just for one group of people or single person, but for a group of people, the whole of India. So we define a democratic loss function where the y, that is the actual value that we have observed, should be close towards this predicted value. Xi is the input, and the assumed predicted value is f of xi. That's the assumed predicted value. And the yi is the actual value. So we want this to be close together, square. Now the square has a reason. The square's reason is that, number one, if it's not square, then the positive and negative can cancel out, which cannot really tell you the difference. The difference is kind of the distance. The distance can never be square in negative. So we wanted to square it. You may ask that we could have taken modulus. We didn't take modulus because I will talk about it next part. And this is for just one data point, including the square, and we add it up for the democratic nature. And we have assumed that f is of the format wx plus b. It's a linear equation, and we have input in here, which leads to yi minus this f, this w times xi minus b whole square. And you can see that this loss function varies because yi and xi are all known values. These are all known values. So this loss function is variable based on the different w and b values, right? So therefore, for example, the blue line has different w, the slope and the intercept. The red line has different slope and intercept. The yellow line has different slope and intercept. And based on that, you have different losses, right? For example, you have different losses, right? Because yi and xi are constants. It's already there, like it's a data. And for different losses, you can see that the red one has a minimum loss, let's say. You find out the minimum among all. Now there are infinitely many numbers, infinitely many w and b. How do you find the minimum? You want to minimize the loss, you want to minimize the distance. You want to find the best such line out there. How do you find it? You have to minimize the loss function. And you can see that's where the calculus comes up. This loss function is nothing but a function of these parameters, w and b, the intercept and the slope. The intercept and the slope. The slope and the intercept. W is the slope and b is the intercept. And you have to minimize the loss with respect to the two parameters, w and b. And you need derivatives for that. You know that, right? I'm sure like you all people know this, that you need to find derivatives for minimizing the loss. And since you need the derivatives, you need this loss function to be differentiable. And if you take modulus mod of x, you know it's not differentiable at x is equal to 0. So that is a problem. And we want it to be differentiable, hence we take the square loss function instead of this. This is how you usually fit a model. Now, for different model assumptions, for example, if you take fx to be, let's say, w1x square plus w2x plus b, you can take it to be that. Now if you take it to be that, the loss function change. The loss function change means it will be yi minus w1 xi square minus w2x. So loss function will be summation of I from 1 to n, the n data points, yi minus w1 xi square minus w2xi minus b whole square. Now, its loss function is a function of w1, w2, and b, and you minimize it with respect to w1, w2, and b by 3 partial derivatives, and you find out why it's happening. The minimum is happening. Now, you may ask that, oh, how do I know that it has a minimum? It is like a cup function. It's a square function. It's a cup function like this. A cup function, it's called a convex function, always has a unique minimum point. For different models, you just change the function. You just change a function and you find out the best model out there. However, this is just for finding the best function or best model in a particular algorithm. Okay. You may ask that I have this linear equation and I have this, let's say, by fitting this, you find out this y is equal to 1.4x plus 3.7. By fitting this new equation, you find out y is equal to, or y is close, the weight is close like 1.5 x squared minus 1.3x plus 2.3. By using this new equation, you find it out by minimizing all these parameters. Now the question is, which one is better? This is something we will not address today. This is something you need to learn more to understand this. And this is something very important, to compare the model to different algorithms. In this, we are selecting an algorithm. Inside the algorithm, there are various infinite models for different w and b, and we are using calculus to find out the best possible model using a loss function, minimizing the loss function. But you have two different algorithms. Like, imagine that there are two different schools or colleges, and inside there are a lot of students. The best student is this. The best student of one college is this, and the best student of another college is this. How to compare them? It's a totally ball game altogether than finding the best student inside a single college, because you have a single examination format, right? But for comparing two different colleges, you have to do different things, and that is where different training, test, and cross validation comes up. But that is not something we will do today, because we are looking for understanding different types of such models, rather a total unified approach to such models. Okay, any questions out there till this point of time? Then I will go to this picture. Any questions?
Any questions, student?
You can raise your hand, by using the raise your hand feature if you are in this meet. Okay, I'm glad you're understanding, but I think you understand more by asking questions. Don't be shy, okay? I'm just like a student. I'm a student just like you, okay? We are here for discussion. I am not any authority out here, okay? You shouldn't believe me, actually. You should ask me questions. Anyways, I'm glad you're understanding. So, the whole point is to understand here the linear relationship. So, I'm transforming this whole structure into a different format of representation. For every xi, the height, I'm writing the every variable I will write as a small circle and xi in that. And for that, this w is the amount of weight it carries. You can easily understand, if it was 14 instead of x, that means x is a really important part. It's 1.4. Okay, so This W tells you how much weight it carries, the feature carries. So xi is the height, let's say. It has a corresponding weight W, and it is the intercept. It is the corresponding weight B. This is like the extra additional part. And using this two, we add it up to find this final functional form. That is W times x1 plus 1 times B multiplication. And I add it up to get this. This is a functional form. We use this notation to represent such functions, such linear functions. Okay, where the weight on that line tells you the amount to be multiplied with that variable. And this one is the external variable, extra additional part, where no variables attached. It's like extra additional part. We get the final functional form. So you can understand in some sense that this is kind of the predicted value, and this is the kind of the actual value, actual weight. This is the predicted weight, and this is the actual weight. P for predicted, A for actual. And we are finding that how close they are or how different they are by a loss function. Now this is just for individual data. So for individual data, loss function is how much y, the actual one, is far away from the predicted one. The actual value is far from predicted value. And as I told you, it's democratic in nature. So we are adding up all the loss functions, all the constants, all the votes of every people. This is kind of a vote, a numerical vote, that how much it is close, how much they want it to be close, how much the actual and predicted is close. And we add it up to find a democratic loss function. And we want to minimize it. This is exactly the whole representation of everything I have told you guys. Now I'm using this representation because it's useful. Okay, it's easy to visualize based on the features, and it's easy to generalize. Okay, I hope all of you understood. Any question out here, guys? Any question? So we have discussed about a specific model which is called linear regression model, and we are representing it in a very specific format. So let me show it to you in a bigger way. So you have the xi, the feature, the height. It is a weight attached to it that tells you how much important it is, and you have another extra variable one to which a weight b is attached. It's an external effect, effect which is not dependent on the variables, and together they are summed up in a single circle, which is, which you can see it's the addition of all the impacts from all different features and non features, and the f of xi tells you the predicted value, yi tells you the actual value, and you're understanding the difference by this loss function, and we are adding it up to find the final loss function. Okay, this is the whole idea, and we are minimizing this loss function by using calculus. The whole goal is to represent different models in this aspect. Okay, now let me go to the multiple linear regression. In multiple linear regression, we are looking at a slightly advanced data set where the predicted is the price of cars, and the input are different properties or features of a car: fuel type, number of doors of the car, driving number of vehicles, or type of driving wheels, sorry, engine size, horsepower, the engine power, the peak RPM, and the city mileage. And based on these features, you have the price. Now let's consider ith data point. So these are x1, x2, x3, x7 are the features, and y is the output, the price. I'm just renaming it in the algebraic form to have a better nomenclature, better abstraction, because abstraction helps you in generalize things and solve problems in a multiple dimensions. And the ith data point can be represented as, for the ith fuel type, I represent it as x1i, and the ith data point of the number of doors I represent x2i, and so on, and the till x7i until the ith price. So understand, it's all the loss function is always democratic. Okay, so we will be finding the loss function for a single data point and we will add it up, and we will represent the functional form of a single data point only. Okay, now observe that you can write this in this format. Now the xi, the x1i, the ith data point, that is the fuel type, its effect on the prediction, like consider it as, or on the price, is w1. Its effect, the x2y, is the x2's variable, x2 variable's effect is w2. Now understand, this w1 w2 is like all constants, or not constant, I mean they're same for every data point. That's the assumption. We want to capture the basic optimum relationship. For the third variable is w3 dot dot till wn, and we are adding it up just like the previous one. Here it was just one variable. Now you have multiple variables, 7 variables, and we have an intercept form, which is like the effect independent or different from the features effect, some external effect, and we add it up here to get the predicted format, right? So it's a wi tells you the impact of each such variable, and we get this functional form, which is called multiple linear regression, because there are multiple linear functions with different features. And this is the actual value, this is a predicted value, and we create a loss function which has number of unknowns. Loss function is unknown is w1, w2, wp, dot, 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 wp and b, and we create this single data point loss function as this. That means for different wi's and b, you will get a different loss amount for each of the data set. Then you add it up. Similarly, then you use calculus to find the minimum, right? You can use calculus to find the minimum in exactly the similar way, right?
Yes, sir.
Thank you, Ayush, for replying. It's good to have you here. So you can see that multiple integration is nothing but an extension of this diagrammatic picture. You can see beautifully how it can help us in making this diagram very precise, very beautiful, optimum, to be honest. And then we add the final, each of these individual loss function to get the final loss function, which we minimize actually. Now, supervised learning can be of two different types. Number one, a simple, regression type. Out is like the a numerical feature like weight, height, price. But if you remember the wine data set, the output was class identifier, type of wine. Whereas variable, the y, is of categorical output. Is of one, or let's say the company's name. One is not categorical, but we have, it's called one-hot encoding. That's a different thing. We'll come to this question later on. But they are categorical. They are discrete in nature, with no sense of ordering. Like you cannot say, okay, this wine is from company A, that wine is from company B, that wine is from company C. So you cannot make an order, like you cannot say this is 1, this is 2, this is 3. Okay, that's not the way it should work. But I have mentioned it just for illustration purposes. So where the output is categorical, that is called classification. Okay, so we have talked about how to deal with regression here, because outputs is regression. A few types of models. Now we'll talk about how to deal with such classification models where the output is categorical, where the output is discrete, and words and no sense of numbers in there. So let's say the output is, something discrete, no sense of numbers out there. Let's say words or company's name. You do not, you know, you do not output the company's name. What you do is that you model the chance of the output to be that company. You model that. Why this is helpful? Because if you this chance, the idea of probability comes in here. The chance of the output being company A, the chance of the wine type to become of type 1, the chance of the wine type to be type 2, the chance of wine type to be type 3. If you want to model, we want to model this. Now, can anyone see that why do you want to model in this way? We want to model chance and not just type 1, type 2.
Sir, because it kinda impossible. What I think is kinda impossible to just have to say that this. Suppose an example A is just
Mhm.
a type A of this. A type. This is the company A of is the product. It's kinda impossible to say if because sir, suppose we train a data.
Mhm.
At the while training the data, we and while we train it completely by doing some training modules, but when we input a new data, it completely cannot say सर कि ये तुम्हारा इसी का पार्ट में आता है सर it
Sure.
it's become not possible to say until unless कि आपका डेटा उसी ट्रेनिंग डेटा के अंदर से हो. So that's why we are trying to find the probability. It give us more what can most probabilitical answer, most reasonable answer than
Yes,
just to
absolutely.
justify कि एक particular part है.
Absolutely. Very good answer, Ayush. Thank you for being the first participant to interact. And yeah, absolutely. So we cannot say something for sure. However, there's another reason to it. That's really one of the most important reasons. Another reason is that since this chance is a number, we can borrow the methodologies of regression, because chances are a number. So you can apply regression ideas that we have discussed out here to we can borrow those ideas to solve this problem too. But there's a small problem. Let's discuss that. So let's take an example. So there are two aspects. One that Ayush has said, that we cannot always say that it's surely of type 1. What we can say, okay, that we cannot say like it will rain today. No, we cannot say that. Or it will not rain today. We can say, okay, the rain chance possibility is 80%, or 20%, or 1%, or 99%. But we cannot say that. I mean, if you have more than 50%, probably will take out your umbrella, or take your umbrella with you. Otherwise, not. Let's look into this data set. This data set is from Wikipedia. So where there are different students and their study hours and passing and failing has been recorded. So there are 5 students data. It's being shown. There are many students out there, but yeah. So you can see that people 10 hours studied and the person passed. And you can understand that the lower the time of studies is, the failing chance is more. Now, how can you model this? You want to understand the idea of passing and failure from the study hours. You want to model the relationship between passing and failing from the study hours per week. Now, as I have talked about, what we can simply do is that we represent passing as 1 and failing as 0. And you can see we can plot this on the graph. And what we can say is that, okay, let's fit a linear model that we have learned because these are numbers. Let's fit a linear model. And we get, okay, kind of this linear model, this linear regression is good. However, this is a very major issue. The major issue is this, that since we are trying to model the probability, the chance of failing and chance of passing, this linear line, the output can go beyond 1 and go below 0. Okay,
Yes,
it
sir.
can
Yes,
go
sir.
beyond 1 and go below 0. So we need to transform this green line, this f of x, this green line, into probability, that is something between 0 and 1. There are many ways to do that. One way you can say that, okay, let's say you get the line to be 2 plus 3x. So you say that, okay, probability of passing is equal to, or you can say, yes, is equal to 1 if 2 plus 3x is greater than 1, is equal to 2 plus 3x if 2 plus 3x is between 1 greater than equal to 0. And if it becomes less than 0, we say 0. I hope you can see. I don't know whether you can see or not. Now, what does this mean? That you're transforming this green line into this format. Anything more than 1, you're collapsing it to 1, that is making the probability 1. Anything less than 1, less than 0, you make it to 0. You all collapse it to 0. You collapse it to 1, everything greater than 1. And in between, it's a probability. It's a good model. It's a reasonable model, but it's not differentiable, you can see at this points.
They are not
So we,
continuous. Yes, those are indifferentiable. Yes, sir. They have
yes,
points like this.
absolutely. And this is a major issue because we need to minimize the loss function, as you have understood.
Yes.
So we need to transform it into a different type of function, which gives you a probability. And one of them is, I will talk about it. There are many candidates for that. So as I have told you, that if you want to use the same structure, you input the x and the impact of it. You input the 1, the extra probabilities between 0 and 1. So how do you deal with it? What you do is that you transform this value by using a function after this. For example, a function like this. This is a function, right? This function says that this is 1 if z is greater than 1, z if z is between 1 and 0, and 0 if z is less than 0. This is a function which transform it between 1 and 0, right? Similarly, there are many other functions like that. And this is exactly called activation functions. This changes the linear into nonlinear according to the problem statement. This is called an activation function. This activation function has a link to a neuroscientist point of view. I will talk about later on. So we are transforming this linear equation, this linear regression, into a probability. We want to do that. And we are using the activation function. So the output is nothing but sigma of f of x, not f of x. That is sigma of wx plus b. And we are comparing, that is the output, that's the probability, because sigma of this wx plus b is between 0 and 1. And we have actual probability, the y. Now understand, this actual probability is not the probability because y is already you have observed. Either it has occurred or it has not occurred. Either it's passed, so it's always probability is the 0 or 1 there. Okay, this value is always 0 or 1. But this value is a probability, so they're trying to match them. Now the loss function is very different from the regression loss function. We are not talking about the loss function today. Okay, we're talking about the model structure. Can we make a unified theory of models? That's the idea. Modeling structure, the functional format. All of you understood this? Any question?
No, sir, not till now, sir.
Okay. What about others?
Yes, sir, we understood.
Great. Thank you, Kushal bro. Any other questions? Any doubt?
No, sir.
Okay. Thank you, Bhuvan. Superb. Let's move on to the next part. So we want an unified model representation. And this is a unified type of structure. So let's understand this. So the input data is, so what we're doing, we are not writing the ith data point. As you can understand that for every data point, the input, every data point, the structure is the same. And then you finally add the loss function to find the final loss function. So for every data point, you have input variables x1, x2, x3, x4, x5. Now it can happen that in this case, there are study hour, there is just study hours. It could have happened whether you studied in your home or campus, whether which time you studied. Okay, there can be other variables too. Probably morning study is good. I'm just it's a hypothesis. And you can input a lot of variables, a lot of features out there, right? So that will make it multiple features, and that's why you need this approach. X1, X2, X3, X4, X5. And we add their weights, Wi, and we make this unified approach, as you can see. And then we have a activation function. Now, can you say that for linear regression, what is the activation function? Anyone?
Sir, can you please repeat what is linear regressions?
In the linear regression, where the output is summation of Wi xi plus b, what is the activation function?
So activation will be
Think slowly, carefully. So the activation function input, you can see is summation Wi xi plus b, and the output is fx, which is also summation xi Wi plus b. So what will be sigma of z? Which function the input is same and the output is same?
1.
So
Maybe
if you
0 will be, sir, because we are adding, no?
think carefully, you're inputting into a function, into a machine, a value, and the output is the same value. Input, if it's a one function, the input, whatever it is, output will be 1, right? So if you input 2, it will be 1. But if we want the input to want 2 and the output also 2, we want the input pi, the output should be pi. We want the input 7,000, the output should be also 7,000. Which function does this?
So it's the linear y equal to x function.
Perfect. So for sigma z, activation function is equal to z. For linear regression, the input, the activation function is sigma z is equal to z. Okay, you can think in this format. All of you understood this? Can give a thumbs
Yes,
up.
sir.
There's a thumbs up button out there, the reaction button out there. I will do it once for you like this. Great. Yeah, I think this is a very better way out. Okay. So the input is, so in linear regression, the input is, the activation function is sigma z is equal to z. And similarly of the loss function. And loss function is different for regression and classification, different aspects. And you add all these loss functions together to find the final loss function, which is minimized. Okay. This is the whole idea of this structure. Okay. Now for logistic, this is now for this kind of function, this kind of classification, one such sigma z, the activation function is taken to be 1 plus 1 by e to the power minus z. So let me try to go to just give me a minute. Desmos. So if you try to use, let's say you try to plot 1 divided by, yes, Nitish?
Sir, will you please repeat that last that you said that Z when we give the input and when we apply the activation function, we will get again the same input.
Yes, absolutely.
And sir, why we need the activation there?
Yes, in linear regression
Uh,
or in
yes,
general.
sir. In general, sir, as you said, na, that last just the last function we are getting in linear, that whatever input we are giving, and after applying the activation function, we already taking the same output, same
Yeah.
input and same output. So why we need there the activation function then?
Yeah, very good question,
If
Nitish. So we do not need the activation function. What I'm saying is that it's a unified approach. So if it's algebraically represented like this, okay. For classification, we are getting this sigma z to be very important because it turns into a probability. But we are looking for a unified approach, a unified algebraic approach. So this activation function, if we even consider it for linear regression, it's just sigma z is equal to z. That's what I mean. Okay. From algebraic perspective, from an algebra point of view. Did you get it?
Okay.
Yeah. In linear regression, we do not need an activation function. But it's essentially its output and input is same. So why do we need it? Exactly. Why will we use our computer memory? But it's for, we do not use that while programming, okay? By the way. But I'm just explaining to you from a understanding point of view.
Okay, sir.
Okay. So now for logistic regression, we take the activation function to be 1 plus 1 by 1 plus e to the power minus z. And you can see that this is one such function I have plotted out. Okay. It's between 1 and 0. You can prove that limit x tends to infinity, it's 1, right? X tends to infinity is 1 by 1 plus e to the power minus infinity. E to the power minus infinity is 0. So it's 1 by 1. 1. X to the power infinity is minus infinity is e to the power infinity, 1 by 1 plus e to the power infinity, which is 1 by infinity, which is 0. In limiting format, I mean. There can be other functions too. So let's try to find out. There's something called tan h. And you can see it's e to the power z minus e to the power minus z by e to the power z plus e to the power minus z. Remember? So e to the power x minus e to the power minus x.
Sir, I guess in Desmos you can directly have tan h function.
Oh, seriously? Oh, thank you, thank you. I didn't know
I
that.
think, sir, this functions,
Let's see.
functions and can, I think there has some tan inverse I have seen, tan h. Yes, sir, yes, sir, there is this.
Very good. Superb. Great. So you can see tan h is between minus 1 and 1. However, you can make it into 1 and 0. If a function is between minus 1 and 1, it behaves similarly. Y is between minus 1 and 1. You can add 1 to it, so it will be made between 0 and 2. But we want to gap it down to 0 and 1, so we divide by 2. So you see, this is another function which makes the probability can go between 1 and 0 if you want to use the probability aspect. Okay, there are much more layers to it. I'm not going into it, but if you want to transform it into a probability, this is it. This is one such way. So activation functions can be of many types. The use is just not doing probability. There are many aspects to it, but one example is making into a probability. Okay, so I hope you understood activation function. It turns a linear function into a nonlinear function for better modeling purposes, for better classification. Now, I've already talked about an unified model approach. All of you understood it. Give a thumbs up if you understood. If you have a doubt, please ask me. Okay,
Understood, sir.
great, Nitish. Thank you for interacting. Okay, now let's try to understand deep neural networks. Like, what is, how is this related to deep neural network? See, deep neural network are originally designed to mimic the brain. So I have this book called This Computational Brain. You can see. I don't know if you can see it or not. Just give me a minute. I'll just. This book is Computational Brain, and you can see it's been written by. I don't know if you can read. Seznoski.
Sinovsky, yes, sir.
This guy has a very important role to play in the history of deep learning. So deep learning neural networks were developed in the hands of neuroscientists in 1950s. They created a deep neural network to mimic the activities of a brain. And they failed in a way that they didn't know how to optimize it properly, and also computational power was not good. Understand that deep neural networks was born in the hands of neuroscientists, and they collaborated with computer scientists to to program it. Unlike statistics, which was developed in the hands of mathematicians and statisticians, there was no brain involved with it. They wanted to find patterns in data. Both are two different fields and both are two different path of approaches. So deep neural networks were developed to mimic the brain activities. And Seznoski is a neuroscientist. So after 1950s, deep learning went into total a phase of zero research. People were not interested in it, except a few people. In one of them, Seznoski is one of them. Along with Geoffrey Hinton, he along with Seznoski developed Boltzmann machine and revived the entire field of deep neural networks in the 1980s. And I will show you the books that are important. Seznoski's book gives you a very deep, I learned all this history from his book of called The Deep Revolution. And it tells you that one suddenly, like, they were doing research, and one day Hinton at 2 a.m. in the morning got a call from a funding agency that they really want to fund their research in deep learning. And it's 1985, I guess. And everything is history then from then. So there was a high time where research was going on. It went to a deep, a black hole phase, and then it came up by this funding opportunity. And then came Hinton, Sosnowski, and then came Jan LeCoul, who is a vice president of the AI Meta of Meta, AI head of Meta, and he did the convolutional neural networks. Okay. So let me make you understand this image, left hand side LHS image is from the Sosnowski's book of Deep Revolution. So you can see it's a ganglion cell in brain, and you can see that the above the green lines are the inputs, the dendrites of a neuron, and it passes through that neuron, and the output, the orange line, is the output. And you can see on the right hand side that the information from other neurons comes in from the dendrites, and it goes out via axon to other dendrites to other neurons. So a mathematical model is like input is 1, this is the dendrite, it's added, there's a bias to it. Bias is to consider the cases which are not included in the dendrites thing, the other aspects, right? Other bodily aspects out there. And the output is summation, it's biased, and the output is this, which is again going into other neurons. So this is how the whole structure of neural networks were developed. Now, I have been taught neural networks, people taught me, like the workshop I was mentioning about, from this aspect. Okay. But I really didn't understand, because it was a computer scientist point of view, computational point of view. But I really want to understand from the current models, basic models we learn from that point of view. That's why I took you, into a journey into neural networks via those more simple models of linear regression, logistic regression into neural networks. Why? Because I think from that point of view, you will be able to understand it better now, because you know these models, those basic models from before. And you can see how this whole structure, this X1 is the information from neuron 1, X2 is the information from neuron 2, and this every feature is kind of a new information, and it's going into a new neuron where the computation is happening, the summation xi and bi, and it goes into another neuron, the output neuron. This is a single structure. So logistic regression and linear regression is nothing but a single neuron input output. Okay, a single neuron. This one is a single neuron input output. So multiple neurons input, and it's coming to a single neuron. The output is from a single neuron. This is a very simple model. So linear regression, logistic regression, actually, which were developed by statisticians, but actually nothing but a neural network. This is absolutely beautiful when I found it out, because both were approached in a very different ways, right? One by neuroscientists, one by statistician mathematicians. So they're thinking in the same exact manner. Okay. In fact, the summation thing is nothing but the first model of how a neuron works in the brain. It's linear regression. So it's absolutely beautiful to see, because both of these two, me, as I have, written in my small short bio, that me being from a statistics background as well as from a computational background now, can understand both the dimensions, and it's so surreal to understand the relationships between them. As I have told you, deep neural networks are designed to mimic the activities of the brain. And this is by Jan LeCoul. His work, he is a person who developed convolutional neural network. He was a person who first did digit recognition, like from very scratch, using every line of code. Now you have Python modules. He developed those Python modules. Okay. So what it means is that human brain works in a different manner. Human brain first sees something, it goes in the retina, and then it stays for 30 to 50 milliseconds in the LGN region. Then it goes to V1 region, then it goes to V2 region, and each region It evaluates some features, some patterns inside each of the data. So what exactly it means is that there are layer of neurons out there. Okay, there are layer of neurons, input and output. The layers of them. What do I mean by layers? Let me explain it to you. By layers, I mean this. X, it goes into multiple neurons. Again, it computes. So there are layers and layers and layers and layers and layers, because that's how human brain works. And this exactly, the hidden layers are being. See, me ask that why a hidden layer? Because they are being motivated by the neurons structures out there. And that's how the hidden layer comes, the concept of hidden layers, because they are hidden in the brain, which you cannot see. And finally, you can see that goes the AIT, and then it goes the PFC region, prefrontal cortex, PMC, MC, the motor command, then it goes to spinal cord, from where you go the fingers, you get the information to the fingers, and you can see the total timeline required for that. One important aspect of machine learning people, of this deep neural network people, is that they want to mimic the brain. And you may ask that why did we consider this simple model? Because they want to mimic the brain. Okay. And brain happens fast. You can see how fast it happens. The whole thing probably happens in a few seconds. And they want in real time the real machines to operate that in that few seconds. They want to build the mind of a human being, and they want it to happen in a very few seconds. That's why after coming here in this electrical engineering department, yeah, Nitish, I'm coming to you. I have realized that how much, yeah, I'm coming to you, Nitish, 1 second, okay? After coming into this electrical engineering department, I've realized how much research goes into not just this modeling of like reducing the time, but also how it's done in material science to build better chips out there to for transistors to make the computation fast. And it is not just being a software side, also the hardware side, there's a lot of research going on, okay, so that the computation happens in the corresponding same rate. And by Moore's law, probably by 2020, 2045, 2050, it will be able to achieve this accuracy. Like within 20, 25 years, it will be able to achieve this accuracy of human brain. That's what's predicted. And it will happen in this real time, probably. So the main takeaway from this is that learning in the human brain works in different layers, and different layers have different activities. And they want to mimic this, and that's why the hidden layers in the deep neural network comes. This linear regression, logistic regression are just one layer, but actually it works in multiple layers. Yes, Nitish, your question.
Yes, sir. As you said, the network we have designed to mimic for the brain, it has multiple layers. So as our brain works too much faster to respond anything we want to perform, but due to having the too much hidden layers, we are performing in that particular pattern. So how we will manage that time? Because
I
our
didn't get
brain
you. Can
works
you
in
come
millis.
again?
Okay, I'm telling that, sir. In our model, there are many hidden layers, uh, which takes time to perform some tasks, right? And but our brain works too much faster. So how that model will manage to conflict that time gap?
See, as of now, we are trying to mimic the brain. We will be able to do it in next 20, 30 years. That's what I have told.
Oh,
Okay.
okay, yeah, yeah.
But as of now, we are okay with real time, like within 1 minute, it's fine. 5 seconds, 10 seconds, 17 seconds, 20 seconds, it's fine. But it shouldn't take 1 hour. And also understand that we have our DNA, okay? Our memory is there for thousands and millions of years. If you eat, okay, if you eat food, let's say if you eat mango, okay, if a parrot eats mango, it remains parrot. If a human being eats mangoes, it remains human being, right? It doesn't change, right? It doesn't become a mango, or a parrot doesn't become a human being. So it has the memory, it has learned all these features of billions of years. So this is called transfer learning, where so essentially your DNA is this transfer learning. Okay. Where it already using the information. So I don't know whether must be using ChatGPT. I don't know whether you have experimented with that or not.
Yes, sir.
But
Use
there
that.
is something called tuning, right? And there is something called pre-trained network. So we are all trying to tune. So this pre-trained thing is essentially from OpenAI, or if you're using Bard from Google, they're already pre-trained. This pre-training of human being, it's like the human being doesn't have to learn by experience that how to eat, or if it eats, the body doesn't have to learn that this is how you should become a human being. It has learned for the last millions of billions and thousands of years how to become it. So human being is nothing but the evolution is nothing but a transfer learning from the past. And that's why a lot of memory is inside you. Okay. Inside your whole body, every single cell, there is memory out there. Because every single cell has transferred, learned. The whole DNA of yours has transferred, learned for the past billions of years. And the extra things you learn, the cognitive abilities is now the new training that is happening. You learn how to write A. That's why it's hypothesized that the new evolution of human beings will happen in the cognitive ability, not the body abilities, because the transfer learning has happened from the past billions of years. So new, because you're learning in a new cognitive way now. So you're learning in a new way. And therefore the new evolution will happen in the aspect of the mind. Okay. And that's why you need to be very stable in your mindset and be capable enough to keep your mind safe, happy, and useful. Yeah, Nitish.
Sir, will you please tell again that what is right now the accuracy of that neural network model compared to the
Which
brain? Neural network, this whole
okay?
neural network model compared to the brain.
Understand this training takes time. Okay, training always will take time. The training takes a lot of time. There is no difference in accuracy. Human beings have been able to, machines are working better in visual tasks than human beings now. In 2017, machine has surpassed human beings. So machines are becoming much more better in this by more training and training. What I said is the computational aspect. The computational aspect, by Moore's law, by the exponential increase of the power of transistors. I'm not sure. It's called transistors, right?
Yes, sir. Yes.
Yeah. Because I'm from electrical engineering background, so I may be saying something wrong. By 2050, it will be able to achieve the level of human mind accuracy. If there are other aspects of environment, human, other heat generation, all these things are taken into account. If the progress is in a similar manner. Okay, but there's something more I have not talked about. Let's talk about it. The universal approximation theorem. Now, why this modeling is important? Why this deep neural network really works? Is the mathematics behind it? Why brain works? So it has been shown that by just one single hidden layer, you can approximate any function of deep learning. Any function on the planet. Any smooth function, I should say. Now, how I am not going to. It's not. I will tell you from where to learn it, but this is one very important thing. That's why the form of a neural network is very, very fundamental. This is really useful. That's what I wanted to mention. Like using a proper number of hidden layers by experimentation, you can easily find it out which really works, which model really works, and which model really approximate the actual situation. You can actually approximate a function. Okay. Now, one important thing is that remember that you need to calculate derivatives for minimizing the loss function. Okay. And this is the last part of it. So, and this is the most mathematical part. So keep a bit of patience here. And this is where the idea of backpropagation comes in. You need to calculate the derivatives for minimizing the loss function. And I will teach you how to do this just for basic linear regression. Okay. Not linear regression, logistic regression and linear regression together, that multiple framework. Okay, I will just take one input. So the input is X, you can see. Now this diagram is not really helpful for understanding this whole minimization using loss function of using calculating derivatives. So you can see X is the input, the output is here, the output is X, Yx plus B. And then there's a composition of functions, sigma Z, and out. Let's call this O. This is defined like this. And then there's a sigmoid function. And the output is, if this is O, this is sigma, this is sigma of O. So it's a composition function. Okay. It's a composition of functions. And this final output is sigma of O. And here there is Y, and we are calculating the loss function, which is a function of this, which is loss function itself function of this output function F. So there are multiple composition of functions. Okay. X to O is dependent on X, and then F is dependent on O, and L, the loss function, is dependent on F and Y both, but Y is constant. The parameter here, the unknown here, is F. Now, can you tell me how do you calculate, what rule do you use to calculate the derivatives of composition function of functions? Dash rule is used to calculate derivatives of composition of functions. Yes.
Sir, we just do the single derivative and equate it to 0. It's that we use.
Yes. Okay, let me give you a better example. F of g of x, if you take the derivative of it, which rule is used to calculate the derivatives of this function?
Chain rule.
Perfect, chain rule. So we use f dash of gx times g dash of x, right?
Yes, sir.
So backpropagation is nothing, but you can see first there is x, then there is O output, then after that output there is F, which is sigma of O of. Now that is for this O, the model, this is the unknown, the B and the W are the unknown. So there is O, X, then is input, the output is dependent on W and B. And then using this output, there is sigma of O, there is a function. And then there is a loss function, which is dependent on, this is called F and F. Okay. So it's a composition of functions. So loss function is nothing but L of sigma of O, which is nothing but O of X, W, and B. So it's a composition of functions. And we need to find the derivative of the loss function with respect to this green, the B and the W. We want to find the derivative of this with respect to this. So what we will do, we will use the chain rule out here, simply. So we want to find this del L of B. So what we do, the immediate relationship, the impact on the loss function is the F. So you need to write down the loss functions, right? The derivatives in the computer, right? So what we do, we just differentiate with respect to the just previous variable, which is it is directly attached to. So the loss is directly attached to, the L is directly attached to F. So we first do the derivative with respect to F. So L is equal to nothing but Y minus F whole square, Y minus output, the functional output whole square. That's the loss function. So we do the derivative of it, dl df, which is nothing but Y minus F whole square is with respect to F. Y is a constant. So dl df is nothing but this 2 goes down, and minus F derivative is nothing but minus is coming out, and Y minus F. All of you understood dl df? Yes or no? Give a thumbs up.
Yes, sir.
Everyone should give a thumbs up if you have understood this dl df thing. What about others? Okay, great. Now The DLDF is calculated. Let's move on to the next derivative. The DF DO. This is the O, this is the F. Now this DF, the F is nothing but what? F is nothing but sigma of O. Sigma is the sigmoid.
Activation function.
Yes, the activation function. So DF DO is nothing but sigma dash of O. Okay, sigma dash of O, which I've calculated here. All of you understood this? Give a thumbs up or write yes in the comment box, whatever works for you.
Yes, sir.
Now next comes the next derivative. Now this output is dependent on B and W both. These are the parameters. Now we are going down this. So we first started from loss function to this. That's why it's called backpropagation, by calculating the derivatives. Now we do DO dB and DO dW. Now DO dW, O is nothing but Wx plus B. So DO dW is nothing but X, right? If you do DO dW, this B is constant, so W gets, W times a constant is like a constant. Derivative of the Wx, Wc with respect to W is nothing but that constant C, which is the X here. So dW, DO dW is X and DO dB is 1, right? Because this is a constant. So this DO dB you have calculated. Now DL dB is nothing but first you differentiate with respect to DL dF, then del L def del O, the output, and del L del. This is nothing but the chain rule, right? And that's how you calculate the derivatives of the backpropagation derivatives with respect to the parameters W and B. This is for just simple simple logistic regression. You can do it for multiple logistic regression, and for that you need to have vectors. You need to know matrix calculus out there. For hidden layers, it's nothing but more and more layers. So you have to just backpropagate it, and every layer there is a weight. So you have to backpropagate the weights out there to find the derivatives. And this is exactly how it's done. Okay, all of you understood this entire aspect of backpropagation, chain rule, and how each and every derivative is calculated for this simple logistic regression? Yes or no?
Yes,
sir.
absolutely.
What about others? Any doubts? I'm mostly concerned with the second year people. Are you guys understanding? Is there any second year people out here? Because they are the youngest of all.
Sir, they are listening to you from the live YouTube link. We are all third years and fourth years present here in the panel.
Okay, thank you. Okay. So yeah, I hope they're understanding on YouTube, and I would love to hear the doubts, and I would love to clear them if they can somehow communicate with me. I will give you my LinkedIn account. You can just get in touch with me or my email ID. Okay, so the basic understanding is this, that to finding the derivative with respect to the parameters, you need to go back and back and back using the basic idea of chain rule and find the loss function derivative with respect to the parameters. I just explained to you with with zero hidden layer out there, but you can do it with more hidden layers, and you need matrix calculus and a lot of things for that. This is just for demonstration purpose, the basic idea, the fundamental idea required to understand and know this. Okay, what else? What else do you need to learn? Because 2 hours is not at all enough. 1.5 hours is not at all enough to understand everything out here. So what else do you need to know about? You should learn matrix calculus for doing the derivatives of a matrix with respect to another matrix. You need to learn how to optimize for loss function, because you will see that in many cases, for example, the loss function for classification, you will see it's called something called cross entropy. I don't discuss this, but the basic idea is that every one of them cannot be minimized using derivatives, just derivatives and equating it to 0, because the derivative often is in the loss function is of the summation form, right? The summation form. Due to the summation form, you cannot separate out the parameters out, the parameters out there equal to 0 and find the solution. You need different numerical analysis methods. Newton's method is one of them, but there is something called gradient descent method, which is another topic altogether, and its variants. And also you need to find the derivatives. That's for sure. So therefore, to find derivatives for one or more hidden layers, you need matrix calculus application, because as you can understand in this example, you have a vector input, okay, and you have multiple w's out there. That's a w vector and b. So you need derivatives with respect to a matrix, a vector, and that is something. And for more hidden layers, it's derivative with respect to vectors with another vector. So you need matrix calculus to learn that, and that's not possible in today's class. I just explained it to you with a very basic example. Also, we have talked about how x1, x2 are numerical inputs, but we have not talked about how x1, x2, what will happen if x1, x2 are categorical features or mixed features or ordinal features like hot, cold, warm. What do you do then? There's something called one-hot encoding for the categorical features, and dummy encoding, other encoding are there, which is another topic altogether. What is the loss function for classification of categorical outputs? We have talked about cross entropy loss function, but there are other loss functions too. Are there any other activation function? Are there any other uses of activation function apart from probability? Yes. What are the different type of activation functions? Why are they important? Why are they not important? What are the cons of it? And how every con led to different activation function, new activation function. For example, there was sigmoid. There's softmax activation function for probability. There's ReLU function, because sigmoid takes a lot of time for computation. And also there's something called vanishing gradient, ReLU function. But ReLU function is not differentiable. Also, ReLU function has also another in the x less than 0, it's 0. So we have leaky ReLU. But leaky ReLU is also not differentiable. So there are functions which are taken to approximate or make the ReLU function differentiable, close to ReLU. So you need to know the story behind each of these activation functions, how they develop, why they developed. Then there's batch normalization, regularization, train test, cross-validation, machine learning workflow, how the entire system is built and why it's built. You should know each and every one of them, and you should be absolutely curious. Now, how to do this? Of course, ma'am can ask me to share my insights in another discussion session. But how many can I take? How many can ma'am take? How many can HIT take? So you should learn something from the books, and no amount of video recording, no amount of someone teaching you can explain you this. Today's lecture was just to inspire you and tell you the story as much as possible in very fundamental mathematics, so that you get inspired by it, you like it, you understand the fundamentals are not so hard. Probably I can learn it to give you the motivation, to give you the throttle to push your learning ahead. So you need books, and I will tell you therefore my 7 favorite books of deep learning, which you can use it. I already posted on LinkedIn, and I have shared it from beginner to advanced and a historical perspective. The deep learning revolution and this book, The Computational Brain, are the historical perspective, both by Sosnowski, as I have told you about that great guy, the neuroscientist. He's at Salk Institute. If you want to pursue a PhD or a research career in computational neuroscience, which is very much the electrical engineers out there who are interested in machine learning can think about, because brain signal is nothing but electrical engineering, a signal, a electrical impulse. So you should start learning, start understanding history. Now, this book by Michael Nelson, it's beautiful. I have given the link out here. You should check out that link. In that book, it's really in that it has a blog, and also he has a book. Just search it online, okay, and you will get the book. Most of them are freely available PDF format. And in this book, it's done by animations, how each of the universal theorem of deep learning the neural networks is applicable. You can also start learning from deep learning, the beginner's book. For the intermediate book, deep dive into deep learning, it's also an online book. A lot of programmings and architectures, and the programming aspect is dealt into. It's really beautiful book. In fact, I realized after I started teaching deep learning, after I took a few courses out there, I realized that the book actually shares the view almost like mine. They have started a linear regression, logistic regression, and then motivated neural networks. So it's good to see professors we are thinking alike. And now the advanced these two books, Jan Goodfellow is a person who did the generative additive model, GAN, generative adversarial network, the GAN. Yoshua Bengio is also one of the most top people out there, along with Hinton, to develop deep learning in 1980s, 1990s. I think he won the Turing Award from 2018. And Simon De Prince, he's a professor and he has written this beautiful book. But this too advanced, you need more mathematics to be learned. So I think you can start with the beginner or the deep dive into deep learning. For learning the mathematics, there's something called machine learning for mathematics, or machine learning for, mathematics for machine learning, or mathematics for deep learning. Let's search it. You can use that book. And I really like that book. Yeah, this one. This one is a pretty good book, and you should be learning from this book, The Mathematics for Machine Learning. You need to learn calculus, linear algebra, probability, and statistics. I will tell you why each of them is required. You have understood calculus is required to minimize, optimize the loss function. Linear algebra is required because every data point, whether it's an image or a signal, can be represented as a vector. And you need to analyze the vectors, the pattern in the vectors, to find the pattern in the data. So, and the analysis of vectors is called linear algebra. For probability and statistics, you have not encountered any one of them today, because I just focus on the modeling aspect. But probability and statistics is used to model the uncertainty in data, in the prediction, the uncertainty, because you don't know how much certain you are for tomorrow, right? We don't know. We want to model it as much as we can based on past data. And that is where the probability and statistics comes up. Okay. So these three dimensions, the uncertainty modeling using probability and statistics, the vector modeling using calculus, linear algebra, and the minimization modeling using calculus. These three together makes up the entire IT of machine learning, deep learning, statistics, whatever you want to say, data science. Yes, Nitish, you have a question?
Yes, sir. One question regarding that. What will be the consequences based on the learning rate? Maybe that if the learning rate is too fast or learning rate is too slow, then what will happen?
Yeah, that is very important question, but people do not know about learning rate. So learning rate is an important aspect in gradient descent. To those who know about gradient descent, learning rate is nothing but like a step size. Okay, so you are moving down a hill. Let's say you're moving down a hill. So there's a valley like this, and you're moving down a hill, step, step, step. If you take the learning rate too small, you will reach the minimum, the bottom point, but very slowly. But if you take the learning rate too high, that is, take the step size too high, let's say a giant is walking, okay, then he may or she may miss the step, miss the minimum, right? A big step, so you may miss the minimum, right? You may come close, but you may miss the minimum. So you have to experiment it out to understand which learning rate is ideal. That's why there are variants of gradient descent. Adam optimizer, momentum, all this, which specifically focuses on also optimizing learning rate, along with like it optimizes that which how much step. So for example, when you're far away from the minimum, you can take larger step, right? But when you're close to the minimum, you should take smaller step. So it's the model already learns, the minimization algorithm already learns, or not learn, but understand that based on the steps at the minimum, the closure, the minimum is the more shorter the steps it will take. So it learns from that. So there are variants of the minimization algorithms, optimization algorithms out there of gradient descent that are done in this manner. Also, there's a new research dimension that is opening up. In fact, I'm the professor I'm working with. He wrote a very good review paper on this, and in fact, he was one of the starting point. He started an aspect of this. It's called deep learning unrolled. So this what essentially is done is that this whole system of deep learning, this neural network is being unrolled into a optimization. Okay, into a optimization algorithm, in a sequential algorithm, where every sequence n to n plus 1 is nothing but one hidden layer computation. And using this sequential algorithm, you can actually also learn the learning rate because it's a parameter in there. So it's a different, it helps. So this is a new research dimension that is being happening right now. But yeah, this learning is a very important question. I hope I answered too much for your question, but I hope I gave an idea of it. I hope you understood, Nitish.
Yes.
Okay. Any other
Yes,
questions?
yes,
Further?
Yes, yes.
Great. Okay. So you can, of course, please, I would love to get in touch with you and discuss with you because I love to share my ideas, and also I would love to learn from everyone around me. And I'm sure the questions you ask, the doubts you ask will be immensely helpful for me to enhance my understanding and also your understanding. It's a mutual thing. And that's exactly how I have learned all these years, from the students, from the discussions, from everyone around, by asking questions and listening to questions. So feel free to contact ma'am, or you can just go to, I don't know, I will just show you probably. Go to LinkedIn and you can just search out here, or you can just search LinkedIn Srijit Mukherjee. I'm not sure if I will be. Yeah. So you get the first one. You can just get in touch with me. But I receive a lot of requests, so it's a kind suggestion, also request that please write a note. Yeah, thank you for sharing my contact. Please write a note that you have attended this RTCI thing, so that I can recognize you, because I am not interacting with every one of the students. I can also not see you, so I cannot also recognize you from your DP. So please get in touch with me and ask your doubt. I would love to answer your doubts, and hopefully we can learn together and contribute something to deep learning, machine learning, and also you can contribute back to India, to the world. And I hope you enjoy this session. Anything else? No, okay, nothing else. Okay, it has gone to the initial beginning. So thank you guys for, it's almost been 2 hours. So thank you guys for staying till this point of time. And yeah, thank you everyone for asking your questions. Thank you, professors and HIT, for the invitation once again. Yeah, thank you.
Okay. We thank you, sir. Your expertise, passion, and dedication to your work were evident in every word you shared, leaving a lasting impression on all of us. Your presence made
Thank
our
you so much.
program more insightful and engaging, and we are truly thankful for your valuable contribution.
Thank you
Also,
so
sir,
much.
we deeply appreciate your commitment to being a part of this workshop despite the time difference, I must say.
Yeah,
I,
I'm really excited. It's 5:30 a.m. here. It was, so it was really yeah.
yes, sir. So, a big thank you to you from all of us.
Absolutely. I would like to know if I can get the recording on YouTube.
Yes, sir. It's available on YouTube. We'll share the link with you. It's
Thank
being
you so
live
much.
streamed.
Thanks. Oh, that's great. That's great. So thank you
Okay.
so much. And yeah, I mean, I would love to hear all of your doubts from all the students out here. I would love to interact. And I would love to visit HIT when I visit India, and yeah, and meet all of you. Yeah.
Sure, sir. Sure, sir. Sir, I want to thank you once again, sir. As I'm a final year student, I have learned about this deep learning thing or some supervised learning, logistic learning, in my semester classes, sir. In I have 6 semester and I have learned all about this. But sir, what you have taught in this 2 hours workshop, sir, is just put cherry on the cake, sir. It is.
Thank you.
It feels so fabulous to learn from you, sir. I just can't, sir. Our teachers taught us so well, no doubt. There is no doubt denying that. But your expertise and your insights bring so much to us, sir, that we can't comprehend any of that, sir. And
Thank you. Thank you.
sir, I have also a question, sir. There's a very fundamental question, sir. I don't get to know, sir, how you put all the data and parameters, weight parameters, which you have seen in deep learning neural network models, into the system, sir. I mean to say, sir, you have taught in PPTs that we have put all the weights and parameters in the neural network, sir. Um, I am there, sir.
Yeah, I'm listening. I'm listening. Yeah.
So, sir, I don't know, sir. I want to feel those ki how you put all the data to the machines in real life. These are all PPT. I can learn from the PPT that you are putting the data and weight setting parameters. But how in real life you all do this? Well, because I am from IT background, I know how to take inputs from a system, how to do output in this all this. But in deep learning, I cannot relate with that. Sir, can you
Okay.
please show some insights on this?
Yeah, absolutely. Very good question. I appreciate this because asking these fundamental questions is important. So how do you input data into your system?
Sir, in I am a C++ programmer. I just take
Yeah,
int
please tell me
declare
like
variable
C plus
and
plus way.
sir, so we just declare variables. For example, say x. So I just say we decide first of all what data type it has. So, for example, I want to take input in integer data type. So I just write int space x semicolon, as semicolon is must in programmer's life. And we just say cin and take the input operator and write the variable name. That's all we have to do, sir. And just do some operations, arithmetic calculus, nevertheless, and we just output it using cout functions. Or
Great. Remember that every such function, everything out there in Python or everyone is dependent on C. It's written in with C. Now coming back to how is data is converted, how is the input into the system. This the answer when you will learn to this right now, you will understand the importance of linear algebra. How linear algebra is so useful. So it's every data point, the whole data set is inputted as a matrix. Okay. Like the matrix you cannot see, but for example, every data point is nothing but a vector. So let's say you have an image, you unwrap the image into a vector like this. And when you stack the vector for multiple inputs, it becomes a matrix, right? And all these computations are done internally by the Python modules, okay? You don't have to worry about that. But every data point is a vector. That is something you should know. Every data point is nothing but a vector. There's a module out there, Python module out there. When you input this data point, x1, x2, x3, x4, xn, this is for a single data point, a single person have features x1, x2, x3, x4. It's input in this module. Output is a loss function. And this is done for all the data points. It's added up. So it's exactly done using vectors and matrices. So therefore, linear algebra and operations turn out to be very important out there to define such things. Okay.
linear
Did
algebra
you?
is most
Yeah.
important to.
Because every data point is stored as a vector. Okay. It's not just variable. It's in fact one of the fundamental variables or variables in higher level language is array. So it's all stored in array, and that's why NumPy array, pandas data frame, all these things are very important. But array is nothing but a vector. Okay, so it's all computed using arrays. Yes. So linear algebra is the way to represent the data set. You're absolutely. It's a very important question. Yeah. Did it answer your question?
Yes, sir. Absolutely, sir. Thank you. Thank
Okay.
you so much, sir.
Yeah. If you have more questions, please let me know. Okay. I would love to answer that in my LinkedIn. Also, I will give my email ID here. Uh, oh, I'm sorry. The second one. Also, I would appreciate if students out there in the live, Shania, if you can share my LinkedIn profile there, probably, or my
Sure.
email ID, they can get in touch with me. Yeah,
Sure, that will be taken care of. Okay.
absolutely. Thank you so much, guys.
Okay.
Any other question? Any other way I can help you out with?
Guys, any questions? Please drop in.
I think no, sir. You have answered all our queries so
Absolutely.
effectively, sir.
Absolutely. Yeah.
Okay.
So read the books more, have more doubts, and please feel free to disturb me if you think in that way. I would love to clear your doubts. Yeah. So
Okay. Thank you so much, sir. It was really a
absolutely.
pleasure to have you. So,
Same here to have all of you.
and okay, we are going to keep in touch with you
Absolutely.
and hope
Please
you
do.
visit us soon in HIT.
Yeah. I would love to. And please keep in touch with, I will keep in touch with all of you. And the reason is that, we are a community of people, and this is a very important time for India to go to the top of this information technology. And you are the future of that. I am also the future of that. So we should do it together. And I would like to play my role as in a very small possible way I can. You should play your role too. So that's it.
Sure. That means so much, highly motivating.
Yeah.
Okay. So now, as we come closer to the closure of this event, I now invite our Honorable Head of Department, Dr. Somen Paul, to deliver the vote of thanks. Professor Paul, over to you.
Hello, I am audible.
Yes, sir.
Yeah. You're audible.
So, good evening, uh, our honorable speakers and all the participants. As all good things come to an end in life, so in the RTCI workshop, autumn 2023, on behalf of Department of Information Technology of Haldia Institute of Technology, I took this opportunity to propose vote of thanks to those who have directly and indirectly contributed to this seminar on recent trends in computing and informatics, that is RTCI 2023, organized by Department of Information Technology. At the outset, I extend a very hearty vote of thanks to our honorable speakers, uh, Dr. Devashish Jana and Mr. Srijit Mukherjee, for enlightening us with their knowledge. Mention our deep sense of appreciation for all the members of organizing committee and volunteers for their unflinching support and coordination. I immensely thankful to Sania and Ayush for their efforts towards anchoring of 2 days of workshop. I also wish to express my gratitude to the principal of Haldia Institute of Technology, registrars, deans, and all others of this institute. My heartfelt thanks to our students for their active participations. Now, I would like to extend my thanks to our uh, speaker, our speaker, Dr. Devashish Jana, in the first session for his inspirational and motivated speech over exclusively about the uh, artificial creativity in a new liminal space between machine and human, between productivity and creativity, which may affect which may affect the lives of billions of workers in the coming years. Dr. Devashish Jana narrated the various aspects and advent of AI application such as heuristic search, Turing test, healthcare, self-driven cars, banking and finance, surveillance, social media, educations, gaming and robotics, AI-driven virtual assistants such as Alexa, Google Assistant, Siri, etc. He discussed exclusively how the AI-driven merge by providing information setting reminders, controlling smart home devices. He also reviewed the AI application for predictive analysis, telemedicine, cybersecurity, ethical medicine, ethical machine learning, agile process architecture, and the adverse sides of AI. But the question still arising whether the AI is exploring as a danger in human race in future. My answer is to be very optimistic and think AI is our blessings in our life. As I am concerned, digital life is augmenting human capacities and disaster-driven systems have spread to more than half of the world's inhabitants in ambient informations and connectivity that offers previously imagined opportunities and unprecedented threats. As an emerging algorithm driven by AI continues to spread, will people be better off than they are today? I would like to express my sincere thanks to Mr. Srijit Mukherjee, who delivered the speech about machine learning and deep learning. Your thoughts have enlightened our minds and have shown us a new path.
Thank you.
Intelligence and computer science that focuses on the use of data and algorithms to initiate the way that humans learn and gradually improving the accuracy. Mr. Srijit Mukherjee shared his thoughts about how machine learning works, starting with data acquisition, data preprocessing, data fusion, data transmission. He narrated machine learning methods such as supervised and unsupervised learning with nice bit of examples, derivations, solutions, and with the accuracy. He reviewed in details the different techniques in machine learning, such as simple regressions that are being used for predictions and classifications. And he also described all those things with the use of activation functions and unified model representations. Our honorable speaker, Mr. Srijit Mukherjee, also explained the architecture of deep neural network, such as input neurons, hidden neurons, and output neurons for training and learning the dataset to achieve the knowledge base that we really deserve. He demonstrated in a right way to compute the output in backpropagation neural network, that is BPN, that being used. So once again, I express my sincere thanks for your mind-blowing speech in this area.
Thank you so much.
Welcome. My my gratitude to all the speakers, my sincere gratitude to all the speakers for gracing the event and sharing their thoughts. Now at the end, I heartily congratulate to all the participants and volunteers for their active participations in this event. Thanks all of you for making this event successful with your contribution and your wonderful staying with us. With these words and kind message, we may move to the end of RTCI workshop autumn 2023. Thank you once again.
Thank you, sir.
Sanya?
So, with this, yes, sir. Thank you so much. With this, we have come to the end of this workshop, and very good evening to everyone. Have a good night, and I wish everybody good health and peace. You may all now log out of this meet. This is Shania Balki signing off.
Thanks all of you.
Chandan. Hello, Chandan.